Hey everybody, I'm Neil, and today I'm going to be teaching you about writing something called half reactions. This is a key component of redox reactions, oxidation and reduction. I would warn you that before we start this video, there's going to be some background information that you're going to want to feel really comfortable with. And I have videos to address those things, so maybe it would be a good idea to watch those first. Firstly, I think you need to understand overall, what does oxidation and reduction mean? Secondly, it's really critical that you understand what oxidation numbers are and how we figure them out. So again, if you don't know those topics before watching this video, please go to the description, click on those links, and prepare yourself for what's going to come in today's edition. Before I explain to you the process and steps we follow to write half reactions, I wanted you to just get eyes on what half reactions look like, so you get a sense of what we're going to work towards as a goal. Behind me, in red, you can see a balanced chemical equation for the synthesis reaction, the formation of magnesium bromide. So in red, we just have our regular balanced chemical equation. Now, beneath it in black, I've written the two half reactions for this redox reaction, the synthesis of magnesium bromide. So let's take a look at these half reactions. How are they different from a regular balanced chemical equation? Okay, the first thing you're going to notice is that in each half reaction, we're really just focusing on one single element that took part in the bigger overall reaction. So for example, in the first half reaction, we just have magnesium. In the second half reaction, we just have bromine. So that's a good starting place. When you write half reactions, each of them, there are two, will focus on just one of the elements in the overall chemical equation or reaction. What's another difference that you see when comparing these to the original equation? I'm sure you've picked up on the fact that we're seeing electrons. In our half reactions, you will always have a certain number of electrons written out. And of course, redox is based on the transfer of electrons, and that's why they're appearing in these half reactions. So in one of the half reactions, we see electrons on the product side, and in the other half reaction, we see the electrons represented to the left of the arrow as a reactant. This will always be the case. In all of your half reactions, you'll have some electrons being produced, and in the other half reaction, some of those electrons being gained. You may also notice that the number of electrons is the same. That's a key feature as well. So now you have an overview, a sense of what half reactions look like, some of the key features. So I think it's time we get into actually looking at examples and breaking down how we go from this to these. Let's figure out how to write proper half reactions for the formation of sodium chloride, which is a classic synthesis and at the same time redox reaction. Now for starters, in red, we have our balanced chemical equation for this process. You're also going to notice that in blue, I labeled the oxidation numbers of each specific element as a reactant and a product. And again, there's a separate video on how to do that. I've also labeled in green what's being oxidized and what's being reduced. So we see that sodium going from a 0 to a +1 oxidation number must have lost electrons. Losing electrons is oxidation. And on the other hand, we see chlorine going from a 0 down to a -1 oxidation number. So it was reduced. Okay, so now we're going to take that oxidation and that reduction and sort of document how they happened in their own separate reactions. Let's start with the sodium first. Here we see we have solid sodium, so I'm just going to represent that as it's represented here as Na. Now, every redox reaction and every half reaction has some typical features such as arrows, right? So we're going to throw this arrow in here. And every time an element is oxidized, we said it loses electrons, correct? I like to think of half reactions for oxidation looking like decomposition reactions. You're familiar with those, right? Those are the types of reactions where you have one reactant splitting up into two or more products. Every time you write a half reaction for oxidation, it should look something like a decomposition reaction. You have your one reactant, in this case it's sodium, and because it's being oxidized, losing electrons, we're going to show that it's losing electrons or sort of decomposing on the product or right side of the arrow. So what do I need to do? Well, first off, on this side, sodium is no longer alone. It's part of an ionic compound. So when I represent sodium on the right side of the arrow, I need to represent it as it is in the compound, which is as an ion, right? So I'm going to write Na 1+. I think you would agree in this ionic compound, the sodium has a 1+ charge, so we need to write that in our half reaction. Now we ask ourselves the question, how would a neutral sodium atom all of a sudden have a positive charge? Well, we know it was oxidized, we know it lost electrons. How many electrons did it lose? The answer is 1. The loss of 1 electron would result in a +1 charge. So I'm going to show that that 1 electron was lost by adding it over here. Okay, so we've got a nice half reaction. We've got our starting material, it's changing or decomposing, and it's doing so in a way where the 1 electron is leaving, resulting in a sodium with a +1 charge. Okay, now remember, oxidation and reduction are tied together. They always occur at the same time. So where did this 1 electron go? Well, it was taken, right? It was taken by the element that was reduced. So let's write a half reaction for that process. We want to show how the chlorine actually accepted the electrons that were lost from sodium and turned into an ion itself. So again, we're going to have an arrow that's very standard. Now again, we always want to make sure that wherever the electron is in our oxidation reaction, which will always be on the right side of the arrow, it's on the opposite side in our reduction. Okay, that's going to be true 100% of the time. Now, on this side, we have chlorine, and it's represented as Cl2. So we have chlorine, Cl2, gaining the electron from sodium. And what happens to the chlorine on the product side? Well, again, you can see it's no longer Cl2. Now it's just Cl that's part of an ionic compound. So it's going to turn into Cl with a -1 charge. I always like to remind students that the law of conservation of matter, or mass, always has to be observed in chemistry. Okay, now we typically apply that to full chemical equations through balancing. But we need to remember that even in these half reactions, that law still applies. What do I mean? What I mean is the number of atoms of any particular kind needs to be the same. And the number of electrons that are lost versus the number of electrons that are gained needs to be the same. So as you inspect these two half reaction equations, you're probably going to notice a discrepancy. I see 2 chlorine atoms on this side because it was the diatomic gas Cl2, but I only see 1 chlorine over here. So what happened to our other chlorine atom? Yeah, it's not okay that there's an imbalance there, so we need to make sure that we represent the 2 chlorines that we began with on the product side as well. Now, there's another issue. If we had 2 chlorine atoms over here, Cl2, they're bonded together, and each one of them gained an electron, resulting in 2 chlorine ions, how could we only have 1 electron being gained? Don't we need 2 electrons? Each one of these chlorines needs to gain 1 electron to create these 2 chloride ions. So this 1 electron here doesn't quite make sense. We need to put a coefficient of 2 in front of that electron. So now we have 2 chlorine atoms. Each one of them is gaining 1 electron apiece, and it's resulting in 2 chloride ions. This makes more sense. But wait, isn't it the case that these 2 electrons that the chlorine is gaining came from the sodium, right? They weren't just added out of thin air. They came from the sodium atom that gave them away. And in my oxidation reaction, I only see one electron being lost. This doesn't make sense, again, in accordance with the law of conservation of matter. If 2 electrons were gained, 2 electrons had to be lost. Now, this happens a lot when we write half reactions. We have an imbalance when it comes to the number of electrons, and we always need to fix that. Fixing it is pretty easy. It's actually easier than the way we fix balancing issues in regular chemical equations. What I mean by that is, when you know that you need to multiply your number of electrons by some number, in this case it needs to be multiplied by 2, you actually just multiply everything in the half reaction by that number. So in other words, since I need 2 electrons, I'm going to put a coefficient of 2 in front of the E, but I'm also going to put a coefficient of 2 in front of the sodium and in front of the sodium ion. We multiply everything by 2. Okay, let's think about this. Does it all make sense? We have 2 sodium atoms. Each one of them gave away 1 electron, which is a total of 2 electrons released, and that created 2 sodium ions with a +1 charge. These 2 electrons were then gained by the Cl2, the diatomic gas, the 2 chlorine atoms that are bonded together. And each one of these 2 chlorines gaining an electron became a negatively charged chloride ion. So far, this makes sense logically in terms of the law of conservation of matter. And I want to show you one other way you can check your work. Your 2 half reactions, well, they came from this original balanced equation, right? So if we put these together, we should get our original balanced equation again. Let's see if that happens. So I'm going to put an arrow down here. And if I add these 2 equations together, on the left side of the arrow, I would have 2Na, also Cl2 plus 2 electrons. Okay, that's everything on the left side of the arrow written now in this combined equation. And let's go to the right side. We would have 2Na plus 2 Cl minus plus 2 electrons. Now, because we have 2 electrons here and 2 electrons there, they would be canceled out. And what are we left with? We're left with 2Na plus Cl2 makes 2Na plus and 2Cl minus, which would combine in the ionic compound 2NaCl. So now we have several ways to check our work. We make sure the electrons are the same on either side of the arrow. We make sure that the law of conservation of matter is always observed by making sure we have the same number of each type of element. And thirdly, we can combine our 2 half reactions and make sure that we get the original chemical equation that we began with. Let's look at another example. Okay, I'm excited to try another one with you. I think having watched the last example, things will start to sink in, and this will make a little bit more sense, I hope. Now, in this case, we're going to be writing half reactions for what looks like single replacement reaction. I think in the last one, it was a synthesis reaction. Of course, both of those fall under the umbrella of redox. I've went ahead and labeled in blue all of the oxidation numbers. So I hope that makes sense to you. And I've also highlighted what's being oxidized. The hydrogen looks like its oxidation number is increasing, so it must have lost an electron. And on the other hand, we see silver is being reduced from a +1 down to an oxidation number of 0. So we're going to be writing our half reactions, one for the oxidation of hydrogen and one for the reduction of silver. So I went ahead down here and I kind of just mapped out the skeleton of my 2 half reactions. Again, there's always going to be a pattern, which is, well, of course, you have your arrows. For oxidation, the electrons will always be a product. They'll always be on the right side. And for reduction, the electrons will always be one of the reactants on the left side because they're being gained. Okay, let's start with oxidation first. So we're focusing on what's happening to hydrogen, just hydrogen, nothing else. So it looks like hydrogen is starting off as a diatomic gas, as it often does, with H2. And we're going to then look at the hydrogen on the right side of the arrow and ask ourselves, what's going on with the hydrogen there? Well, it's no longer H2 as a diatomic gas, right? Now it's part of a compound. So what we usually do with these compounds is we split them up. We think of what's the hydrogen, what's its identity as part of this compound when it's by itself. And that would be that hydrogen has a +1 charge. Okay? Now, how would it go from being H2 to having a +1 charge? Well, when things become positive, they're always losing electrons. Of course, that's what oxidation is. So we're going to need to document that. But I want to get ahead of this and think to myself already about the law of conservation of mass. If there's 2 hydrogens here, how could there only be 1 on this side? That doesn't really make much sense. So we need to balance that. Let's put a 2 in front of the H+. And we know that these 2 hydrogens, each of them loses 1 electron. Well, that would be a total of 2 electrons being lost altogether, right? So we're going to need a coefficient of 2 in front of the He. So we had 2 hydrogen atoms, each one of them lost an electron, resulting in 2 hydrogens with a 1+ charge. Okay, now let's go to the reduction. Now for reduction, we're just focusing on silver. It turns out the sulfur is not going to appear in our half reactions at all. This is very common to have species in a chemical reaction that don't show up in your half reactions. If you want to know why, the sulfur was a -2 in terms of its oxidation number as a reactant, and it's still -2 as a product. So sulfur really didn't participate in the redox, the transfer of electrons, so we completely eliminate it. So let's focus on our silver. Now, silver here is part of a compound, right? And what's it doing in that compound? Well, it looks like it's acting as an ion with a +1 charge. So we're going to have our Ag, and it's +1. Now, on the right side of the arrow, the silver has become neutral. It's got a 0 oxidation number. So there's the reduction, right? +1 down to 0. And the only way that would happen is if you gain an electron, right? That's the only way to reduce a positive charge down to 0 because electrons are obviously negatively charged. So we have this silver, it gained an electron, and on this side, it's just going to be neutral Ag, okay? So we've got our oxidation, we've got our reduction, loss of electrons, gain of electrons. Now we got to start to check our work and ask ourselves, does this all make sense? Now, one thing that probably jumps out to you is the fact that our electrons are not balanced. We had 2 hydrogens, each of them giving away an electron, but down here we're only showing 1 silver gaining 1 electron. So as we did in the last problem, we're going to need to rectify that. And the way I'm going to do that is I want 2 electrons in this reduction equation, which means I'm just going to multiply everything in the equation by 2. Okay, we're not allowed to just go in and add a 2 in front of the electrons alone and say, okay, the electrons are now balanced, I'm done. That's not the way balancing these half reactions works. I know we do stuff like that with regular chemical equations. We can just go in and put a coefficient in front of one specific thing. But in half reactions, if we want that 2 electrons, everything in the half reaction gets multiplied by 2. So we're going to have 2 silver on this side and 2 silver on that side. Okay? So once again, let's just do an overall check. Our electrons are on opposite sides and we have the same amount. That's great. We have 2 hydrogens and 2 hydrogens, 2 silvers and 2 silvers. Okay, I love it. This looks wonderful so far. Remember, we can always do a little combination, add these 2 reactions together to see if we get something similar to what was happening here. Now, I should warn you, when we add these 2 together, we're not going to see the sulfur, right? And that's okay because the sulfur did not participate in the actual redox reaction. So if we do that combination, we'll draw an arrow. On the left side of the arrow, we have H2 reacting with 2 Ag plus 2 electrons. On the right side of the arrow, we have 2H plus reacting with 2Ag and 2 electrons. Okay, now the electrons again would cancel out because we have the same number of electrons on both sides, so we eliminate those. And now we look at what's left and we ask ourselves, does it generally match up with what we saw happening up here? Again, with the omission of the sulfur, right? So we had H2, we see H2. We have 2 silver ions, and here we have 2 silver ions that are part of this compound. We're just not seeing the sulfur there. On the right side of the arrow, we have 2 hydrogen ions. Here they are. They were part of this compound here. We have 2 regular silver atoms. And so overall, everything checks out. We've got our 2 half reactions for this redox situation. Okay, let's give you one to try on your own so you can check for understanding. So here's your comprehension check. I'm confident you're going to get this one right. We've got a reaction where hydrogen gas and oxygen gas are forming water. This is a redox reaction. I want you to take a moment, pause the video, assign oxidation numbers, identify what's being reduced and oxidized, and then see if you can write the 2 half reactions for this process. Come back and check your answer when you're done. Okay, thanks for doing the work and coming back to check your answer. It's practice that's essential to make sure you've nailed down this skill. Now, these are the 2 half reactions. Did you get them right? Do you have a question about how I got these answers? You can interact with me and I can answer those questions if you just leave a comment below. I'll respond as soon as possible. Now, of course, this has all the features of half reactions that we look for. Firstly, we have the same number of electrons being lost and being gained. And of course, they're always going to be on opposite sides of the arrow. We also make sure that the number of each type of atom makes sense. 4 hydrogens, 2 oxygens, and 2 oxygens. Okay, you want to try just one more? Let's do it. Okay, we have a classic single replacement reaction. Take a moment, pause the video, and try to come up for the half reactions. Come back and check your work. Here are the correct answers for this problem. Did you get it right? Remember that if you do have questions or concerns, you can always interact with me by dropping them in the comments section, and I'm more than happy to give you some extra help using that method. Thank you for watching, and congratulations on putting in the time and effort to try to learn how to write half reactions. If you've got a moment and could like the video or subscribe to the channel, I always appreciate that support. Okay, have a great day, and I hope to see you again in the next video.